Hey team, hope everyone's doing okay. I've gotten a lot of requests already, so I'm just going to try to go through the whole thing. Let's start with number 30. So we have two functions, f and g, and we want to know where they have parallel tangent lines. So I'm not really interested in graphing these two functions, but I would like to graph their derivatives. If I'm doing it by hand, then I would literally just find f prime and g prime, set them equal to each other, and find out where f and g have the exact same slopes. It's where f prime and g prime equal one another. But since I'm allowed to cheat and use a calculator, I'm just going to jump ahead and do that. I just graphed secant squared and 2x. That's f prime and g prime. Graph those, and I also narrowed my window to just 0 to pi, since that's what we're looking at, right? Yeah, 0 to pi. So I see it looks like they're only intersecting right here, so let's cheat. 2.08. 2.08. Looks like the answer is B. Cool. Psst, hey, come here. I want to know who's really watching these videos. So, the first 10 people to send me today's code word are going to receive extra credit, and some of you need this extra credit. Today's code word is hammock. You send me the word hammock either through Remind or email, I'll get you some extra credit, but shh, don't tell anybody else, okay? Alright, let's get back to the review. Okay, here on number 32, this is a good example of a calculator problem that really can't be done on the calculator. Only about half of the calculator questions really can or should be done on the calculator, you'll find. And here's one that really, calculator doesn't really help us much with this problem. So I'm going to do the whole thing by hand. So we have a function, and we want to know where its derivative is equal to the average rate of change. Okay, now remember the concept here. As long as a function is continuous and differentiable over an interval, then the secant line connecting the endpoints, the slope of that secant line represents your average rate of change. So we want to find that slope, the slope between our endpoints. And then we obviously also want to find the derivative, and we'll set that equal to our average rate of change to find when our instantaneous rate of change is the same as our average rate of change. Now, that concept seems easy enough. The problem is we have some weird interval from A to B. They're not concrete numbers, and that probably makes your head hurt a little bit. So I'm actually going to do this problem twice. Once, I'm just going to make up some numbers and try to understand the concept, and then I'll apply it to these vague A and B boundaries. So here's our problem done with I just made up an interval from 1 to 5. We have our function, and forgive me, I used x instead of t. F of x is 1 over x, and I'm just going to find the average rate of change over the interval from 1 to 5. Step 1 is finding the actual endpoints. So plug 1 in, and we get 1, 1. Plug 5 in, and we get 5, 1/5. Find the slope between those endpoints. That's easy enough. The slope is negative 1/5. And then we take the derivative, which is negative 1 over x squared, and we set that equal to our average rate of change. You solve for x, we get x equals root 5. So it turns out at x equals root 5, our average rate of change is, or our instantaneous rate of change is equal to the average rate of change over the interval from 1 to 5. So if that makes sense, then you're just going to do the problem again, but instead of using 1 to 5, I'm just going to use A to B. So I don't know what A and B are, but whatever A is, its y value is 1 over A. Whatever B is, its y value is 1 over B. So the slope between those two messed up points is negative 1 over AB. So I'm going to set our derivative equal to that weird nonsense and solve for x the exact same way I did before, and I get x equals root AB, which hopefully is an answer. There you go. A. Make sense? Okay, number 33 is another one that where our calculator isn't really going to help us very much. You just have to understand what all this stuff means here. So we have some function. I don't know what it really looks like other than it's definitely positive. It is increasing and it's concave up. Now, A is the actual area under the curve between some unknown interval between A and B. L would be some numerical left Riemann sum approximation. R is going to be a numerical right Riemann sum approximation. And T is a trapezoidal approximation. And we're just based on what very little we know about the function, just that it is positive, increasing, and concave up. We have to figure out what order those approximations would come in. So I sketched an example of an increasing and concave up function. And this first picture here would represent the actual area. So that would be A. The actual integral from A to B of f would be the actual area under the curve. A left Riemann sum would just, I know it just says it's broken up into n subintervals. It doesn't really matter. You realize that no matter how many rectangles I break this up into, it's going to be a low ball figure because it's going to miss a whole bunch of these little areas. So a left Riemann sum is definitely low. A right Riemann sum is going to be high because no matter how many rectangles I break this shape up into, the left side of every single rectangle is going to jut out from the shape or from the curve a little bit. So it's definitely going to be a high ball figure. A trapezoidal one, I know that looks kind of exact. Also, I didn't label this T before I took the picture, but I know that looks pretty exact, but there is a little extra area at the top of every single trapezoid. So this one's also high, but not quite as much as any rectangle Riemann or any right Riemann sum is going to be. So L definitely looks like the lowest. A is exact. T is a little high and R is very high. So I'm going to go L-A-T-R. L-A-T-R-A. Okay? Okay, here we are, number 34, where we have R of T, a rate function that represents the rate at which water is leaking out of the tank. And let me just check the units here. It seems to be in, I would assume, gallons per hour. So R is already gallons per hour. And I want to know how many actual gallons leak out of this tank in the first 3 hours. So the first thing you're going to do is get rid of A and C. Those are trash because I don't like the R prime. I'm not integrating R prime. I want to integrate R. If R T is already in gallons per hour, then integrating R gets us back to gallons. R prime would be the derivative of gallons per hour. If R is already gallons per hour, then R prime is gallons per hour per hour. And integrating that just gets us back to gallons per hour. So that's not helpful. I want to integrate gallons per hour to get back to just gallons. And clearly the bounds are 0 to 3. That's our only option, but that makes sense. I'm going to integrate over 3 hours to find out how the net change in the water in the tank, I guess, how much water was leaked. Now, I don't want to divide by 3. I don't want 1/3 of that. I just want to do D. I want to integrate from 0 to 3 the gallons per hour function. So I think that's easy enough. Your answer is D. Okay, 35. Another calculator question you're not going to use a calculator on. You have a composite function, h. H is f of g, and you want to find h prime of 1. So step 1 is going to be figuring out what h prime is in terms of x, which is going to be in terms of just f and g. So forget all of this stuff for right now. You just want to go off to the side and figure out h prime. If h is a composite function f of g, then make sure you're using the chain rule to find the derivative of h. H prime is going to be f prime of g, don't change the inside stuff, and then tack on the derivative of the inside stuff. So the derivative of h is f prime of g times g prime. So h prime of 1 is going to be what you see here, f prime of g of 1, and times g prime of just 1. And then that's when all this stuff starts coming into play. So g of 1 is 3, g prime of 1 is negative 3, f prime of 3 is negative 5, and there we go, we get to h prime of 1, which is 15. Makes sense? All right, number 36 here, we've got, we're trying to apply the mean value theorem over some interval from 0 to b on a function that is differentiable and increasing. That's all we know about it. So it might look something like this, between 0 and b over the interval from 0 to b. Here's something that is just increasing the whole time. So the mean value theorem states that whatever the slope is between our endpoints happens somewhere on the curve at some point instantaneously. So these 3 points right here represent the places on the function where I think the instantaneous rate of change seems to be parallel to this average rate of change between 0 and b. So what are our options here? F prime of c equals f of b over b. I don't even know. No, that doesn't look like anything. I guess if it said something like f of b minus f of 0 over b minus 0, then that would make sense, but that doesn't seem that. The way it's written, doesn't make any sense. F prime of c equals 0. Well, no. I mean, you can see that f prime of c, each one of these 3 locations could be a value of c. And f prime of c is definitely not 0. 0 would be horizontal. F prime of c is positive. Duh. There's your answer right there. F prime of c has to be positive because the slope between our endpoints has to be positive. We're told the function is increasing. It's the only thing we know about the function. That tells us that f prime is positive all time. So the slope between the endpoints has to be positive, meaning the slope at our c values is also going to have to be positive. But let's just take a look at D. F prime changes at x equals c. No, it's not ever going to change. Like I said before, it's always going to be positive. So your answer has to be c. Okay, looks like for 37, we're finally going to get to go back to our calculator on this calculator section. We have 2 functions, e to the x squared minus 2 and y equals, looks like the top half of a circle. So we want to find the area of the region enclosed by those graphs. So I already went ahead and graphed them real quick, although I think I forgot the minus 2. So let's throw that in. Okay. And, well, we're just going to cheat. Let's do this the quick way. Analyze graph. Bounded area. This should snap right to the intersection point. And there we go. 5.05. 5.050. Perfect. C. Now if you don't utilize the bounded region or bounded area tool on your calculator, then you just have to manually, or I guess just go cheat and use your calculator, find these intersection points, and then set up an integral that goes from whatever that is to whatever that is. And your integral should be these, the red function here, the square root of 4 minus x squared minus this exponential function. And that should give you the same answer. Cool. Okay, for number 38, I don't think you really need a calculator, but we might as well since we have it. You realize that this value is either going to be positive 1 or negative 1. So as I'm approaching, and the drop off or the switch, the jump is happening at 1. So left-hand side, here's our graph. Because I'm coming in from the left-hand side, the y value is approaching or staying at -1 before jumping up to +1. So the two-sided limit doesn't exist, but the one-sided limit is -1. The right-sided limit will be +1, two-sided limit doesn't exist, and the left-sided limit is -1, which is C. Okay, number 39, we have the graph of f prime, and we want to know how many points of inflection f has. So please don't say something like, what is it, 1, 2, 3. If you go with 3, you're not really trying hard enough here. I don't want to know how many points of inflection f prime has. I want to know how many points of inflection f has. The white dots. So, go away. I want to think about what the graph of f double prime might look like. One way to think of this, anyway, is to try to think of what the graph of f double prime looks like. So, we will have the next graph, f double prime, because this is f prime. F double prime will have a 0 right here. Right here. Right here. Right here. Right here. And looks like right here. And the general shape, I think, is going to be a positive fourth powered function. This looks like a 1, 2, 3, 4, 5, like a quintic function. So, and it's positive. So the derivative of that thing will be 1 power less, also positive. So it's probably going to do something vaguely like that. Now, if this is f double prime, you realize the zeros, or more specifically, where it crosses the x-axis, not where it just hits the x-axis. So wherever this thing crosses the x-axis back on the original f, we had a point of inflection. So that happens 1, 2, 3, 4 times. D. In general, f the zeros of f prime. So this is getting a little sloppy here, but here, here, and here, those represent the extrema back on f. So I know I have a minimum here, and a maximum here, and a minimum here. The zeros of f prime are all about the extrema of f, and the extrema of f prime are all about the points of inflection back on f. But if you don't remember that, then you should at least remember that the zeros of f double prime are obviously going to point toward the points of inflection back on f. So I hope that makes sense. Okay, number 40 can be tricky, but it's also very simple. There's only one answer that makes any sense. It has to be A. You're looking for the average value of this curve from 0 to 12. So all of the values are 4, 4, 4, 4, 4, 4, 4, 4, 4, and a whole bunch of other 4s, and then a whole bunch of numbers that are less than 4, and then a 0. So the average definitely has to be somewhere between 4 and 0. I'd say it's definitely probably 3-ish range. It's 4 for a long time, and then it goes down. So the average of all of these y values is probably a little less than 4. It's definitely not more than 4, and it's definitely not 22 or 44. So I'm pretty sure it's going to be A. But if you like doing things the long way, or the right way, I guess, you can use your average value formula. I want to find the area of a rectangle that has I guess it's 12 units wide, and f of c units high, f of c being the average value. And that should be equal to the integral of this weird function from 0 to 12. So you can find the You don't actually have to do any calculus. You can find the integral of this function geometrically. You have a 4 by 8 rectangle, and then you have a quarter of a circle of radius 4. So find this area and then divide it by 12. And I've already done that for you over here on the scratch pad. I'll take 1/12 of the area under that whole curve. You got your 4 by 8 rectangle and then a quarter of a circle of radius 4. So your average y value is going to be 3.7. So there you go, A. In 41, we have a function f. That's an ugly looking function, and g is the antiderivative, or the integral of f. And we're told that g of 5 is 7. We want to figure out what g of 1 is. So I worked a little of this out by hand to show you what we're going to do here. Let me just get my face out of here. So if you think about the relationship between f and g, g is the antiderivative of f. So if I integrate f from 1 to 5, then g, whatever it is, I don't actually have to find it, is the integral of this function. This function would integrate back into g. So the integral of all of this from 1 to 5 would wind up giving me g of 5 minus g of 1. That's just the fundamental theorem of calculus. G of 5 is something we were given, it's 7, and g of 1 is what we're looking for. So now if I just rearrange this a little bit and solve for g of 1 can be calculated by 7 minus the integral of f from 1 to 5. So let's just do, sorry, I left it over here. Let's just throw that in our calculator, 7 minus that integral, and I already worked it out. It's going to be negative 3.88, which is A. Done. All right, 42, a little bit tricky. You got to pay attention to the units here when you're given a function. So A of t is just the amount of whatever the heck we're producing, a certain item producing factor. So given a time value, A is only giving me how many actual products are being produced. It's not a rate function. It's just giving me the number of objects that have been produced. So I'm going to do this the wrong way first. You're probably tempted to just graph your function, and I fiddled with the window until I kind of see everything that I wanted to see, from 0 over to like 15-ish, all the way up to around 650. So you may be tempted to do something like find the max of that graph. And if you do, I mean, thankfully, this isn't even an answer. This just tells us that about 8.5 hours into production, we have produced the maximum number of whatever the heck we're making in this factory, which comes out to around 4:30 in the afternoon, and we're really only supposed to care about 0 to, or I guess 8 a.m. to 4 p.m. So an answer at 4:30 doesn't make any sense. It's not an option here. So hopefully that raised some red flags, and then you rethought about the problem. We're asked at what time the rate of production is at a maximum, not when we have produced the most things. I would assume that we've produced the most things at the end of our workday, unless somebody, I don't know, set some on fire or threw some away. At the end of the workday, we will have produced the most. So that's not what we're being asked. I want to know when, at what time our rate is the highest. So I want the derivative of this, A prime. If this is, let's just pretend we're making toys. This is toys. A is the number of toys we have made, given a time value. I want to know how many toys per hour we're making. So I need the derivative of that. So I want to just find the derivative by hand. That's easy enough to do. And graph it. That's what I want to have. That's what I want to find the maximum of. Now, technically, we should be pretty careful here. I could see just by looking at it, the maximum is right there. But don't forget that we could also have found a maximum at one of our endpoints. So there you go. I won't bother doing this. You should also check a prime of 0 and a prime of 8 to see what the rates are at the beginning and at the end of the day. Now I can see from the graph that the rate at 8 a.m. is definitely lower than the rate at 11 a.m. and that is definitely higher than the rate way over here. This is probably 4 p.m. over here. So t equals 3 definitely gives us our highest rate of production. And then t equals 3 would mean 9, 10, 11 a.m. B. Alright, there's definitely a nerdier way to do this by hand, but this is easy enough on our calculator. You can just graph this really quick. And I'm just talking about this part. You're not going to try to graph like the integral part of it. I just want you to graph this thing. So G is the integral under that curve from 3 to something, from 3 to whatever. So the G would be the integral, or at least for number 1 here. G is the integral from 3 to 5, or I want to know if G is increasing on the interval from 3 to 5. Well, G is the function where I start at 3, and I'm going to start integrating from here to 5, which is right there at the 0. So G is definitely increasing from 3 to 5 because from 3 to 5 I'm eating up all of this positive area. So G is getting bigger and bigger and bigger. So 1 is true. G is increasing from 5 to 7. Let's see. From 5 over to 7, I'm moving forward and chomping up all of this negative area. It's all below the x-axis. So G would actually be going down. It's going up this whole time, and then it's going to start going down because I'm adding negative area into G. And then, so 2 is false. G of 7 is negative. That's going to be false. Because G of 7 is going to be the integral from, if you think about it, going from 3 to 7. You eat up all of this area, and that looks like an awful lot of area compared to this little bit of area that you're going to take away. So this is the integral from here to here is still definitely going to be positive. You could be nerdier about this and do some stuff by hand, but that's the easiest way to understand that problem. You just throw it on your calculator, see what the accumulation function does. Make sense? Okay, 44 is a little weird just because of the language. We have a population that is increasing over time. Here's our weird population model. And they introduced this idea of a limiting value, which will make more sense, I think, when you see the graph in a second. So this population will approach a limiting value as time goes on, just in general meaning that population is going to cap out at some point. For whatever reason, they run out of room, food, resources, whatever, or your population levels out. During which year will the population reach half of its limiting value? So here's your function, and let me get my face out of the way. 6,000 minus 5,500 e to some junk. Okay. So the limiting value is just this idea that clearly your population is increasing over time, and then you see it level out. So the limiting value is, oh no, sorry, I'm going to turn myself up here now. Well, if you just kind of inspect, you can see your limiting value here seems to be around 6,000. It doesn't look like it's going to go above that, which makes a lot of sense, because if you think about this function and the limit as x, or I guess as t approaches infinity, as this gets really, really, really big, then this value is going to get really, really large, but also negative. So now think about what e to a crazy big number is, a crazy big negative number. It's going to be like 2.7 and change raised to a crazy negative number, which is going to make it almost 0. So then this whole 5,500 term goes away, and you're just left with 6,000. So 6,000 is our the limit on our population. So I want to know when our population hits 3,000. That's easy enough. Let's just get out of here. Let's just graph that. See where they intersect. .81. Now here's the other weird trick. Some of you are probably going to be tempted to pick the third year. 3.81 is not in the third year. It's in the fourth year. I don't know if you guys know this, but Shale's birthday is today. He just turned 17, and he's not in his 17th year. He's in his 18th, right, Shale? So 3.81 is in the fourth year. Also, you guys should all jump onto Google Classroom, go to this assignment, and say happy birthday to Shale. Drop him a note. Anyway, I hope that makes 44 make sense. Okay, number 45, we have a weird looking limit. It looks a little like our limit definition of a derivative, but not quite. It's a really weird, like, I forget what they call it, some sort of symmetrical definition of a derivative. But it's nothing we need to know or worry about. We can go about this in a different way without knowing what this really is. So the limit as h approaches 0 of this weird thing equals 6 minus 4x. Okay, well, first let's try to evaluate the limits. If we attempt to plug 0 in for h, you notice we get 0 over 0, which is good news because now we get to use L'Hopital's rule. So I'm going to take the derivative of the top and of the bottom and see if then I can evaluate it. So now I'm still taking the limit as h approaches 0. Now, unfortunately, it's not, I don't know what the function is, so I'm just going to have to write it in derivative notation. Whatever g is, whatever g of x plus h is, its derivative is g prime of x plus h times 1, technically. H here is the variable that we're taking the derivative with respect to. So chain rule applies, and I take the derivative of the inside, the x. I know we usually take the derivative with respect to x, but here we are not. We're taking the derivative with respect to h because that's what that tells us right there. So the x goes away, and the derivative of h is 1. So that's the 1 is there from the chain rule. For the second part here, we're going to do minus g prime of same thing, x minus h. Leave the inside alone. But then the chain rule says take the derivative of the inside stuff. The x again goes away. The derivative of negative h is negative 1. Now the derivative of the bottom is 1. H just goes to 1. And now we're going to try to evaluate again. Plug 0 in for h, and you see we just get g prime of x minus negative g prime of x, or g prime plus g prime, so 2g prime. Now remember, originally they said that that limit should equal 6 minus 4x. So that means 2g prime should equal 6 minus 4x. Therefore, g prime equals 3 minus 2x. Okay, now we can read the rest of the problem here. Which one of these three statements are true? G prime of 0 is 6? I don't think so, because g prime of 0 is 3. The second statement states that g double prime of 0 is less than 0, which is true, because g double prime, the derivative of this, is going to be negative 2. Negative 2 is less than 0, so 2 is true. Then the derivative of that, g triple prime of x equals, or of 0, equals 0. g triple prime of x is 0, therefore g triple prime of 0 is 0, so 3 is also a true statement. 2 and 3 are both true, which means, there we go, C is our answer. Okay, that makes sense. All right, that's our whole review. If you guys have any follow-up questions, shoot them my way. Today is a day 4, so I'm not going to be posting an assignment for you guys tomorrow. Take a day off, rest. You'll hear from me on Friday with a new assignment. Okay, till then, you guys take care of yourselves.